This is lesson number 5 for engineering dynamics. In this tutorial we will look at constrained and dependent motion of particles, so basically pulley systems. The tutorial contents includes an introduction with 1 degree of freedom, an introduction with 2 degrees of freedom, and then we'll complete 5 example problems. So what I have here are 2 particles connected with this cable here. So this is a fixed pulley that I'm calling O. This is particle A, particle B. Okay, so both of these particles are connected to each other by this cable, and as one moves, it's going to pull the other one up the ramp. So first thing we generally want to do in pulley systems is set something called a datum. So a datum is a fixed reference point from which measurements are made. The number of datums usually equal to the number of directions the particles can move in. So if you look here, there are 2 particles and 2 directions. So for particle A, the direction that can move is up and down this ramp, and for particle B, it can move up and down this ramp. So the datums we would set here. So typically we would set the datums at a point where the length beyond which one of them is constant. So if we look at this datum here, this length on the actual pulley itself is constant, its length doesn't change. And if we look at this datum here, on this side of it, there's that constant length again. So if we call these 2 variable lengths, so length sub A, so L sub A is one variable length that is connected to particle A, so we call that L sub A. So L sub A is just this length from the datum to the particle, and L sub B is a length from this datum up to the particle. So the motion is said to have 1 degree of freedom because the configuration of the particles can only be defined in one way. So by that I mean, if you look at one particle, let's say particle B, we can only change its configuration in one way. Okay, so if you look at particle B and think, how many ways can I change its position without moving it directly? The only way would be to move this pulley here, pulley A. So if you move particle A, that's going to move pulley B. So because of that, we say it has 1 degree of freedom. And likewise, if we look at pulley A and think, how many ways can I change its position without directly changing it? The only way would be to move pulley B. So the motion is said to be constrained because particles are forced to move in a restricted way. For example, if one particle is moved, the other will be forced to move, meaning one particle's motion is dependent on the other. So that's what we mean by dependent motion, because the motion of these particles is dependent on the other. And it's constrained because the particles are forced to move in a restricted way. Both of these particles can only move up and down their side of the ramp. So because of that, we say the motion is constrained. So the important thing to note from here is that we always set a datum, which is basically a fixed reference point from which we can make measurements. So the measurements we're making in this case is length A and length B. Okay, so L sub A is the variable length of the rope connected to the particle and up to the datum, and the variable length L sub B is the length of this rope or cable connected to the particle and up to that datum there. Okay, so the length in between the datums, so the length of rope that's actually on the pulley, there's always going to be a section of length on that pulley that remains constant, and that's another thing to be aware of. So we can write the total length of the cable as big L. Okay, so big L here just means the total length of that cable, and that's going to equal to the segments of that cable. So we've got L sub A, so that's this segment here of the cable, L sub A, plus L sub B, which is this segment here, plus L sub CNST, which means the constant length of rope. Okay, I'll be using this notation throughout, so make sure you know what this is. So that's just the constant length of rope on the cable. Okay, so that's this bit there in red. So that is the total length of the cable. Next, we take the time derivative to get velocity. So we take the time derivative of each term in this equation to get velocity. So if I do that for L, I'm going to get 0 because the length of the rope, the entire length of the rope, isn't changing with time. Okay, so that length doesn't change with time, so if we took its time derivative, we'd get 0. L sub A does change with time, so we can write L sub A by dt, because this length here can change. So if I move this down, the length is going to get shorter, and if I moved particle A down, this length is going to get longer. And the same can be said for L sub B. So L sub B also changes in time, so we can write L sub B by dt, and the constant length of rope, its time derivative, is going to be 0, because that length on the pulley, the constant length, doesn't change with time either. Okay, so we put 0 for that. So if I rearrange this equation for L sub A by dt, I get this. Okay, so I'll just subtracted this term from both sides. And then I can write that in a more compact way as minus L sub A dot. So remember the dot just means one time derivative equals L sub B dot. So I'll be sticking to this notation throughout. So make sure you familiarize yourself with that. So the dot just means one time derivative. If I take the second time derivative to get acceleration, I'm just going to get that. Okay, so minus L sub A double dot. So there's two dots, which means two time derivatives equals L sub B double dot, which means two time derivatives. We can also write L sub A dot as V sub A. So the velocity of particle A equals the velocity of particle B, so V sub B. Okay, so this can be rewritten like that as well. And minus L sub A double dot can be written as minus A sub A equals A sub B. So that can be written like this as well. But I will be sticking to the dot notation. Okay, so just be aware that in some textbooks or other lectures, you might see this notation, but they mean the same thing as this. I will be sticking to this notation so that it reminds me that it's the time rate of change of the length L. So if we look at this system here, again, this has 1 degree of freedom, because if I focus on particle A and think how many ways can I change its position without directly changing it, the only way would be to move particle B. Okay, so if I focus on particle A and think how many ways can I change its position without changing it directly, the only way would be to move particle B. And the same thing can be said for particle B. So if I look at particle B and think how many ways can I change its position without changing it directly, the only way would be to move particle A. Okay, so because of that, again, we say this has also got 1 degree of freedom and the particle's motion is constrained. So particle A is constrained to only move horizontally and particle B is constrained to only move vertically. Okay, so we're going to set our datum. We're going to put it here and here. So remember there's two directions. So there's a horizontal direction and there's a vertical direction. So you can expect there to be two datums. So remember before we said the number of datums is usually equal to the number of directions. Okay, so there's two directions, horizontal and vertical, so two datums. Okay, so if we label our variable lengths, so we've got L sub B, which is the length of this section of rope here, and we call it L sub B because that length is associated with this particle here, particle B. And then I'm going to call this length here length D, and I've put it in red because the length from this point here down to here is constant. So I just called that D and I put it in red to tell me it's constant. And the other variable length we have is L sub A, so that is a length from this datum to particle A for that section of rope, and that is a variable length, so I call that L sub A because it's associated with particle A. So I can draw in my constant length. So remember the length of rope on this section of the pulley is going to be constant, so that is going to be half a circle there. Okay, so I can say that length, that is going to be the radius of the pulley attached to particle B, which I'm calling R sub B times pi. So R sub B, the radius of this pulley, times pi will give me its length. So remember the circumference of a circle is 2 pi r, and since we've got half a circle, we'd ignore the 2 and just put pi r. Okay, so that's basically what this is here. And I can do the same thing for this. So the radius of this pulley at point C times pi will give me that constant length, and I can say the same thing for this, except this rope is going over a quarter of that pulley, so R sub A, so the pulley associated with particle A times pi divided by 2 will give me this length, this constant length along that pulley. Okay, and I can also say that the length here is constant. I'd ignore this length here because that's not actually part of the cable. Okay, so when it comes to writing down the equation for the length of the cable, this isn't going to come into it because it's not part of the cable, but this is. Okay, this length here is in red, and that is constant because its length doesn't change with time. Okay, so if I write the entire length of the cable, so remember capital L there just means the entire length of the cable, and that's going to be 2 times L sub B, okay, because I've got two lengths for that, so this length here and this length there are both L sub B. So I'll write 2 times L sub B plus this constant length plus that constant length. Remember we've already accounted for this over here, okay, plus this constant length plus D, okay, which is this length here, plus this length here, so R sub A pi over 2, plus L sub A, plus this variable length, and we've only got one of those, okay. So that is the entire length of the cable. So now what I'm going to do is combine all these constant terms together like this, and then call all of these constant terms in red L sub CNST, which means the constant length of the cable, okay. Because these are all constant, I can just group them together as one constant like this. So next I'll take my time derivative. Okay, so remember, if I take the time derivative of L, so the entire length of the cable, it's going to be 0 because the entire length of the cable doesn't change in time. For this section, I'm going to get 2 times L sub B over dt plus 0, because remember the time derivative of the constant lengths is going to be 0 because they don't change in length with time, plus L sub A by dt, so the time derivative of L sub A. So then I'm going to bring this term onto this side to be left with this, and then again write that out using my dot notation. So minus L sub A dot equals 2 times L sub B dot. So basically what this is saying is that if I move this particle to the left, okay, so let's say if I moved it 1 meter to the left, that means L sub B is going to change by half a meter. So that's what this expression is telling us. If this particle is moving to the left with a velocity of say 1 meter per second, that would mean this particle is going to move up with a velocity of 0.5 meters per second. So then I'll take my second time derivative to get acceleration. That's just going to become minus L sub A double dot equals 2 times L sub B double dot. So basically what the minus is telling us is that movement to the left is going to be negative. Okay, so we're going to say movement to the left is negative and movement upwards is going to be positive, okay, as shown by these two equations. So that is our introduction with 1 degree of freedom. So now we're going to look at 2 degrees of freedom. Okay, so the motion is said to have 2 degrees of freedom because the configuration of the particles can only be defined in 2 ways. Okay, so the way I think about this is that if you focus in on one of the particles, so let's say particle A here, and think how many ways can I change its position without directly changing it. So we could move particle C down and we could move particle D down as well. So I can change its position in 2 ways without changing it directly. So I can say the same thing for particle D. So if I think how many ways can I change its position without changing it directly, I can move particle C down and particle A down as well. It's helpful to label the pulley which connects the 2 cables. Okay, so I'm calling that pulley B. So first I'm going to set my datum. So there's my datum here. And I'm going to label this as cable 1. So cable 1 is this cable. And I'm going to call this cable 2. So that is this cable here. Let's label our length. So I've got L sub A. So the variable length of rope connected to particle A is this length here. So that is the length from particle A to the datum. Okay, so I'm calling that L sub A. I've also got a variable length L sub B. Okay, so that is the length from the datum to the center of this pulley here. And I've got this variable length L sub C, which is the length from the datum to the pulley attached to particle C. Okay, so that is going to the center of that pulley. And I can also rewrite this length as L sub D, which is the variable length of this cable attached to particle D from the datum. So these are all the variable lengths. So just like we did before, we can put in our constant parts of the cable. So the total length of cable 1 is going to be capital L sub 1. Okay, so that is the length of cable 1. So I'll write all its segments together like that, and I'll do the same thing for cable 2. If I look at cable 1, I've got L sub A plus 2 of L sub B's. Okay, so I've got 1 there and 1 there for L sub B. And I've got my constant terms there for cable 1. And for cable 2, I've got this length here plus this length L sub B plus L sub C minus L sub B, which is going to be this length here. Okay, so I'll just do L sub C minus L sub B, which will give us that length. And then I put in my constant terms, so this part and this part. So again, combine all the constant terms together. So for cable 1, I've put these constants together, and for cable 2, I've put them together again. So next we take our time derivative to get velocity. So hopefully by now you're comfortable with that. So I'm just going to do that here and here. Okay, so these are our time derivatives. Okay, so notice how I got 2 times L sub C dot. Okay, because I've got an L sub C here and an L sub C there. Okay, and this is a minus. So we get left with that. And then I'll take the second time derivative to get that and to get this. Okay, so now I've not put the zeros in. So I've just taken the actual bits that are varying. Okay, so this is the expression for velocity of the 2 cables, and this is acceleration for the 2 cables. What I want to do is eliminate L sub B dot, okay, because if I look at these 2 equations here for velocity, L sub B dot appears in both equations, and L sub B is the length from the datum to pulley B, okay, and it's pulley B that connects the 2 cables together. So if I eliminate L sub B dot from here and here, I get one expression relating the velocity of all the parts of the cable. So if I take this equation here and put it down here, subtract L sub A dot from both sides to get this, and then divide by 2 to get that. Okay, so that was for this equation here. So all I did was rearrange this equation for L sub B dot. So next what I want to do is substitute L sub B dot into this equation. So if I take that equation and put it here, just so it's more clear, I'm going to substitute L sub B dot into here, and that will give me this to get this. Okay, and then if I divide both sides by 2, so this becomes divided by 2, and this is going to become L sub A dot over 4, so that will give us this. So the minus there is telling us the direction of particle A and D is opposite to the direction of particle C. Okay, so let's say if I move particle C down, so that would mean it's minus, so that would mean that particle A and particle D would move up, which both stay positive. Okay, so the minus is just telling us that the direction of particle C is always going to be opposite to particle A and particle D. So if we was to apply the same procedure for acceleration, I'd get this. So that is our introduction with 2 degrees of freedom. Okay, so now we've looked at pulley systems with 1 degree of freedom and pulley systems with 2 degrees of freedom. We're now going to complete 5 example problems. So example 1. If the cable at A, so down here, is pulled down from rest with a constant acceleration of 0.75 meters per second squared, find how long it would take weight B, so this weight here, to rise 1.5 meters from the instant A starts to move. Where it says the instant A starts to move, so the point A here, that is basically telling us that point A started moving from rest. So I'm going to label that in, so point A there is pulled down with 0.75 meters per second squared. Okay, so that is a minus because it's going in the downward direction. So I'm going to assign a minus sign to that. I'm going to take that up here, so I know L sub A double dot, so the acceleration of point A here is minus 0.75 meters per second squared. So to get velocity, so I integrate that to get velocity and displacement, or I could use the equations from rectilinear motion. Okay, but I'm going to integrate this. So if I integrate minus 0.75, I get minus 0.75 t, okay, and that is velocity in meters per second. And if I integrate that again, I get minus 0.75 t squared over 2, and that is in meters. Okay, so that is the displacement. But I've just put L sub A because it started off from position 0. And I can rewrite this as minus 0.375 t squared, and again that's in meters, so I'll just do 0.75 divided by 2 to get minus 0.375. Okay, so I've got L sub A double dot, L sub A dot, and L sub A. Okay, so let's set our datum. So I'm going to put the datum there, and I'm going to say the variable length L sub A is the length from the datum to the point A. Okay, so that is a variable length L sub A. And I'm going to call the variable length here from the datum L sub B, and I've got 2 of those. Okay, so this length and this length are L sub B. Okay, there's my constant lengths of the cable. Okay, so the total length of the rope, capital L, is going to be L equals L sub A, so L sub A here, plus 2 times L sub B, because I've got 2 of them here, plus these constant lengths of the cable. Okay, so the total length is L sub A, constant lengths, and 2 of L sub B. Okay, so express as changes in length segments. So because I know L sub A is a variable length, and I know L sub B is also a variable length, I can write them as changes in length. But since L and the constant parts of the cable don't change, I can just put them down as 0. So there's going to be 0 change in L, 0 change in the constant lengths, and I can express L sub A and L sub B as changes in lengths. So L was 0, so delta L sub A is the change in the variable length L sub A, and delta L sub B is the change in the variable length L sub B. Okay, and that was 0 because it doesn't change. So I can then subtract delta L sub A from both sides to be left with this. Okay, so all I did was subtract this term from both sides to get this, and then I'm going to substitute delta L sub A into here. Okay, this is delta L sub A, and we just got L sub A here. I can still substitute that into there because remember this is displacement, but because it started off from 0, I didn't need to put delta. Okay, so if I just substitute this into delta L sub A, okay, the minuses are going to give me a positive value, so I get 0.375 t squared equals 2 times delta L sub B. And now what I want to do is substitute delta L sub B with 1.5 meters, because we are trying to find how long it takes this particle here, so L sub B, to rise 1.5 meters. So we substitute 1.5 meters into delta L sub B, because the change in its length is just going to be 1.5 meters. So substitute that in, and now we want to solve for t. So next I'll just do 2 times 1.5, which gives me 3 meters. Okay, so I'll just rewritten this whole equation here as this. So 2 times 1.5 is 3 meters. I then divide both sides by 0.375 and then take the square root. Okay, so that's this. So divide both sides by 0.375 and then take the square root of both sides to get t. Put that into your calculator, and t is 2.83 seconds. So that is the time taken for particle B to rise 1.5 meters. So 2.83 seconds. If this point A starts from rest and has an acceleration of minus 0.75 meters per second squared. Okay, so that is our answer for example 1. So example 2, find the speed of weight C. Okay, so there is weight C. If weight A moves down with a speed of 15 meters per second. So there's weight A, or particle A. We're treating both as particles. So if weight A here has a speed of 15 meters per second, and we're saying downwards this time is positive, so I just switched it up. So it doesn't matter whether we say down is positive or negative, or up is positive or negative. As long as you're consistent in your calculations, you will get the right answer. So there's cable 1. So this cable here is cable 1. This cable is cable 2. Set our datum. So our datum is going to be put there. There's the variable length L sub A. And I'm going to call this variable length here L sub B. So that is the length from the datum to the center of pulley B. Okay, so pulley B is what connects the two cables. And the variable length L sub C is the length from the datum to the center of this pulley attached to weight C. Okay, so they're all our variable lengths. These are all our constant lengths. Okay, so this length is constant, that's constant, that's constant, this is constant, and so is that. So we ignore this length here because it's not part of any of the cables. Okay, so we can ignore this. Okay, so there's the length of cable 1. Okay, so that's going to be L sub A plus the constant lengths plus 2 of L sub B, because I've got 2 of them here. So that's L sub B and that's L sub B. There's 2 of them, so I put 2 times L sub B. And we've got a constant lengths and the length of cable 2. So L sub 2 is this cable here. So that's going to be L sub C, which is that length there, plus L sub C minus L sub B, which would give us this length. Okay, so L sub C minus L sub B would give us this length here, plus our constant lengths, which is this part and this part. So take our time derivative to get velocity. So I'm going to take the time derivative for each equation for the cables. Okay, so that will give me this. So remember, the derivative of L sub 1 will be 0. The derivative of L sub A will give us L sub A dot, so that's our time derivative. Same thing for L sub B, not forgetting the 2. And this is going to be 0, so I haven't bothered to write that in this time, so that is just 0. This is going to be 0 as well. That's 0. And notice that we have 2 L sub C's here. Okay, so L sub C plus L sub C there. So that's how we get the 2 there. So next I want to eliminate L sub B dot from both equations. So rearrange this equation for L sub B dot. So subtract L sub A dot from both sides to get this. Divide both sides by 2 to get that. And then substitute L sub B dot into here, where L sub B dot is minus L sub A dot over 2. So substitute that into here, and I get this. There's a minus there and a minus there, which is going to give us a plus. Okay, and then also what I did was times each term by 2 to get this term, to get rid of the fraction here. So if I multiply that by 2, they cancel out to leave L sub A dot. Multiply this by 2, I get 4 times L sub C dot. Okay, then 2 times 0 here would just give us 0. Subtract L sub A dot from both sides, since I'm trying to get L sub C dot on its own, because that's what we're trying to find. So I divide both sides by 4, substitute L sub A dot with 15 meters per second, because L sub A dot is moving down with 15 meters per second. Okay, so I'll substitute that into here to get minus 15 meters per second over 4, which gives us L sub C dot, which is minus 3.75 meters per second. So the minus is telling us that this is moving up in the opposite direction to L sub A dot. Okay, so remember we said 15 meters per second in the downward direction, that's going to be positive. So this is going to move upwards in the opposite direction with minus 3.75 meters per second. Okay, so be careful of those minus signs because they are important. And that is our answer for this question. So example 3, find the speed of weight B, so weight B is down here, if the cable at point A moves down with a speed of 6 meters per second. So hopefully you get the idea of this by now, so if you'd like to pause the video and have a go at this question and then resume once you're finished. Okay, so we're trying to find the speed of weight B if the cable at point A moves down with a speed of 6 meters per second. Okay, so there's cable 1, cable 2. So cable 1 is this cable here, cable 2 is this cable there. So set the datum. Okay, so our datum is here. We draw in our variable length L sub A, which is the distance from the datum down to A. We draw in our variable length L sub C, which is the distance from the datum to the center of pulley C. So pulley C here is what connects the two cables together. And then I put in my variable length L sub B, which is the distance from the datum to the pulley attached to weight B. And these are all my constant lengths. Okay, so that length is constant, 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 and that is constant as well. Okay, so the total length of the rope, L sub 1, we're going to write out the equation for the length of cable 1. Okay, so that is going to be L sub 1 equals L sub A minus L sub C. So that is to get this length here. So it's going to be L sub A minus L sub C for that length plus L sub B minus L sub C. So L sub B minus L sub C will give us that length plus L sub B for this length. And that was for cable 1 plus the constant lengths. The total length of rope 2, so cable 2, so you can call them a rope or a cable, it doesn't matter too much. L sub 2 equals L sub C plus L sub B plus the constant lengths. Okay, so L sub C is this length plus L sub B, which is going to be this length here, plus the constant terms. So now we take our time derivative to get velocity of these equations. So hopefully you get that by now. So we get that and that. We have one L sub A there. We have two L sub B's, so 1, 2. And we've got two L sub C dots there as well. So minus L sub C and minus L sub C there to give us minus 2 L sub C dot. Then we found the time derivative of rope 2. Okay, so that is going to be 0. That's going to be 0. And we just get L sub C dot plus L sub B dot. So now we want to eliminate L sub C dot, okay, because they're in both equations. So we've got L sub C dot there and L sub C dot here. So we eliminate those. So we'll just take this equation, rearrange that for L sub C dot to get minus L sub B dot. Okay, so I just subtracted that onto this side. And then what I did was substitute L sub C dot into here. So L sub C dot is minus L sub B dot. So I just substitute that into here to get this. So we've got a minus there and a minus there to give us plus. Okay, so I'm left with this. And then simplify that down to this. Okay, so that gives us 0 equals L sub A dot plus 4 times L sub B dot. And then subtract both sides by L sub A dot. And then divide both sides by 4. Okay, so I just substitute 6 meters per second into here because I know the velocity of the variable length L sub A is 6 meters per second. So I just substitute that into there, divide that by 4, and I get minus 1.5 meters per second. So that is the velocity of this weight here, weight B. And the minus is telling us that it's moving upwards. Okay, because we already said positive is downwards, so we've got positive 6 meters per second. So that means the velocity of weight B is going to be upwards in the opposite direction, so that's why we have that minus here. So example 4. Find the velocity and acceleration of weight A if weight B falls with a speed of 2 meters per second with a constant acceleration of 0.5 meters per second squared. So we're told the speed of weight B and we're also told its acceleration. Okay, so first I'm going to set the datum. So my datum is going to be put here, okay, and it goes through the centers of these two pulleys. And I'm going to call this length here L sub A, which is the variable length from the datum to the center of this pulley attached to weight A. Okay, so that's L sub A as my variable length for this part here. And there's two of those. So there's that one and there's this one. And then I'm going to call the variable length L sub B as the length from the datum to the center of this pulley attached to weight B. Okay, so that is L sub B and that is also a variable length. And then I'm going to call the length from the datum down to the center of pulley C as L sub C, and that is in red because that is a constant. So the distance from the datum here, from the center of this pulley to the center of this pulley, is constant because these two pulleys are fixed on that support. And we can ignore this incline here, just because that's inclined. We can actually ignore that in our calculations. And the reason for that is because if we were to take the components of this length, we'd have one component in the vertical direction, which will have the same length as these two lengths. So the same length as that length there and this length here. So if I draw that in, so that is the vertical component of this inclined bit of length there, which is here. And this is the horizontal component. So this part here is going to stay constant, okay? And this length we can treat in the same way as this length and this length. So we've got 3 of those in total. Okay, so there's my constant part of the cable. So that is also constant, that is constant, this is constant, and this is also constant here. So the total length of the rope is going to be L equals 2 times L sub A plus 3 times L sub B minus L sub C. Okay, so L sub B minus L sub C is going to be this length here. And remember, we had 3 of those. Okay, so we've got this one, we've got that one, and we've got this one here. So that's 3 in total. Okay, plus the constant lengths. And because this is constant, I can group this with the constant length there to be left with this. So next I'll take my time derivatives to get velocity. So the time derivative of that was 0. The time derivative of 2 times L sub A will give me 2 times L sub A dot plus 3 times L sub B dot plus 0. Okay, so the time derivative of this is 0 because these lengths don't change. Take the second time derivative to get acceleration. So we're going to be left with that. Okay, so now we rearrange and substitute. So I'm going to take my equation here for velocity and then subtract 2 times L sub A dot from both sides to be left with this. And then divide both sides by minus 2 to get this. Substitute L sub B dot, okay, with 2 meters per second because I know the velocity of L sub B. So I know the velocity of this weight, okay, was 2 meters per second. So substitute that in to get this. And then simplify that down to get minus 3 meters per second. Okay, so that is the velocity of weight A, and the minus here is telling us that it's going up, since we are told that the velocity going down is positive. So they move in opposition to each other. And that is our answer for velocity of weight A. So now I want to find acceleration, so I'll take this equation here and do the same thing as I did before. Substitute L sub B double dot with 0.5 meters per second squared because we're told the acceleration of weight B is 0.5 meters per second squared. Substitute that in and I get minus 0.75 meters per second squared. Okay, and that is our answer. So example 5. Find the speed of the sliding weight B. Okay, so there's our sliding weight. If the slider A, so here's slider A here, moves up with a speed of 5 centimeters per second. This time we're given speed as 5 centimeters per second. We can see here that the distance from this point here down to this line is 30 centimeters, so that's y equals 30 centimeters. And we're told that the length from the center of this pulley to this point is h sub b, which is 20 centimeters. And we're told the distance from this line here down to this line, which goes through the center of this fixed pulley, is d, which is 80 centimeters. And that is going to be constant. Okay, so d is going to be constant because this pillar here is fixed, this pulley is fixed, and h sub b is going to be a variable length. Okay, so that can change with time. So h sub b dot would be the speed of the sliding weight. So we don't need to do a datum for this. Okay, so there's our constant length here, and there's another constant length there. So the total length of L, so the total length of the cable is going to be L, which is 2 times d minus h sub b. If we do d minus h sub b, we get this length here. And we've got 2 of those, so we multiply that by 2. Plus s, okay, s, which is this length here. So from the slider A down to this point, that is the length S, plus the constant lengths, which is just that length on the pulley and this length here. Okay, so that is the total length of the cable. So I can rewrite S as the Pythagoras of d squared plus y squared. Y is a variable distance. Okay, so that is going to change with time, and d there is going to be a constant. Okay, so remember the length from here to here is constant. So I can rewrite S there as this length squared plus this length squared, and then square root them, which will give us s. Okay, so that's just Pythagoras. Okay, and then I can rewrite this like that. Okay, so if I expand that 2, I get this. Okay, so next I'm going to take my time derivatives. So the time derivative of L is going to be 0 because the length of the cable does not change with time. This is a constant, so 2 times d is a constant because remember d is constant. So the time derivative of that is going to be 0, and then we get minus 2 times h sub b dot. So we just took the time derivative of h sub b to get h sub b dot, and we want to take the time derivative of this. So for this we're going to have to use the chain rule. Okay, so for now I'm just going to say d by dt of square root of d squared plus y squared, and the derivative of this here is going to give us 0. So I need to take the derivative now of s with respect to time. Okay, so remember we said s was square root of d squared plus y squared. Okay, so now we're just applying the chain rule. So we're going to say dz dt equals ds dz, where I'm going to say z equals d squared plus y squared. So I just substituted the stuff inside the square root and called it z. So I need to find dz dt and I need to find ds dz. Okay, so if I do dz dt, again I'm applying the chain rule because z is not given as an explicit function of time. To get dz dt I have to do dz dy times dy dt. Okay, so dz dy, that's just going to give us 2y because this is constant, and dy dt is just y dot. So that's going to give me this. So that is dz dt, and that is 2 times y dot. So dz dy was 2y from here, and dy dt is y dot. And if I do ds dz, remember s was equal to this, and I substituted the stuff inside the square root with z, so I can say ds dz equals d by dz of the square root of z. This comes from where I substituted z into here. So if I differentiate that now, I get 1 over 2 times the square root of z. Okay, so this is the same thing as z raised to the power of a half. So you reduce the exponential by 1 to get z to the minus a half, and then you times that by the original exponent, which was a half, okay, to get this. And then if I take dz dt, which I got here, and ds dz, which I got down here, and multiply these two, so I'm doing dz dt, which is this, times ds dz, which is that. So if I substitute them in, I get this. Okay, so I've got 0 on this side. This is the derivative of ds dt, so this bit here. And then I can rearrange that for 2 times h sub b dot, divide both sides by 2, and then if I substitute z back into here, I get this. Okay, and then if I substitute my numbers in, so I knew y was 0.3 meters. Okay, so I just converted centimeters to meters, and I know the velocity of y, so the velocity, so y dot is going to be 5 centimeters per second, so I just converted 5 centimeters per second into meters per second, and then substitute d in there, which was 80 centimeters, which is 0.8 meters, and then substituted y into here, which was 30 centimeters, which I converted into 0.3 meters, and then put that all into my calculator to simplify that down to this. Okay, so the top there, all multiply that gives 0.015. The bottom here will give 0.85. Multiply that by a half, I get h sub b dot equals 0.0088 meters per second. And that is the velocity of this sliding weight. And that is the answer to this question. Okay, so if you found this video helpful and you would like to practice some more questions, then click the link in the video description. Okay, or you can just copy and paste it into your search engine, or you can manually type the website here on your search engine. So if I just copy and paste the link into here, I'll be taken to this home page. Then if I click courses, engineering dynamics, I come to this page here. So this is the engineering dynamics modular course. So this is the formula sheet, which is a PDF you can just view, and you want to click lesson 5, so constrained and dependent motion of particles. Okay, so this is the free video that you just watched. So this video is the same video we just watched. This PDF viewer here contains all the questions for you to practice. So that's question 5.1, 5.2, 5.3, etc. Okay, and the answers are shown at the bottom. Okay, so the answers are shown here. So this is a downloadable PDF. So if you click this icon, you can download this as a PDF. And down at the bottom you have the course content. All these are are just videos that complete each individual questions on this PDF. And you can watch them in any order you like once you've made the purchase.